So like I said in the previous sections, we're going to put all of our equation solving all together here. What we're going to do is we're going to make use of the fact that exponentials and logarithms are inverses of each other. So if I have 2 to the x versus log base 2 of x, these are going to be inverse functions, and they have to have the same base there. So if we think about it, if we take 2 to the log base 2 of x, basically we're plugging one function into the other. Well, remember that what we're saying is log base 2 of x is equal to something. So whatever this is equal to 2 to the something. In this case, I'm writing y. But the equation log base 2 of x equal to y means that 2 to the y is equal to x. And that's exactly what this boils down to here. The logarithm expression represents the exponent of the base, and so I can replace the logarithm in the exponent with whatever exponent it's supposed to represent, and I should just get whatever's inside the logarithm automatically. Similarly, if I take log base 2 of 2 to the power of x, there we go. Well, this can only be equal to x, because that will mean that 2 to the x is equal to 2 to the x. So in both cases, they have collapsed variable x. So we're going to start with exponential equations, and actually for both of them, what we're going to do is we're going to start with really easy ones and then build our way up to the more complicated ones that require more thought. So I've got a simple one here. I have 5 to the x plus 3 equal to the 1/5. This is an exponential equation because I have an x in an exponent. Now, this one we won't need logarithms to solve because we can just observe that 1/5 is actually 5 to the negative 1 power. So I've got 5 to the x plus 3 equal to 5 to the negative 1. A lot of times books will introduce problems like this to start with and say use the one-to-one property of exponents. And we could just say that since the bases are the same, we must have that x plus 3 is equal to 1. What's happening is once we set this up, 5 to the x plus 3 equal to 5 to the minus 1, what we do is we take the log base 5 of both sides, and we simplify them. So the exponent inside the logarithm comes out in front as like a multiple or coefficient, x plus 3. We have log base 5 of 5, which will just be 1. And I do the same over here. Take the exponent out. I've got negative 1 times log base 5 of 5. And then I could either say, well, log base 5 of 5, yes, is just 1, or I can say I'm dividing them off of both sides. And the result is I have x plus 3 equal to minus 1. Or, in either case, I forgot my minus on the left side, x equals minus 4. So the key here is that I manipulated it, I guess, so that I have the same exponent on both sides of the equation. And that brings us to our next style of problem. We just have a common base exponent on either side. So I've got e to the x minus 2 equal to e to the 3x minus, plus 8. And remember, e is that magic number, 2.718281828. So what I would do here is I could say, hey, the bases are the same, we could just match the exponents, but I like to do log steps. So I say I take natural log of both sides. And in fact, no matter what problem you have, if you just use natural log every single time, you'll get the same answer, because the choice of log doesn't matter because they all work essentially the same. It's just I'm using natural log specifically here because it's going to cancel with the e. And in the previous problem, we used log base 5 because it would cancel with the 5. We got e to the x minus 2 equals natural log e to the 3x plus 8. And I can say the natural log and the e cancel because exponents and logs cancel. So I've got x minus 2 equal to 3x plus 8. And the long version of that step is what I did on the previous page. We first use the exponent property of logarithms. So an exponent on the inside comes out in front, and whatever's left just reduces to 1. That's exactly what happens here when you have a log base e, and e is a base of an exponent. And then we can just solve this normally. So I'll subtract 8 from both sides, and I'll subtract x from both sides, and I'll get, let's see, minus 10 equals 2x. So it looks like x equals minus 5 for this problem. But things can get a little weird sometimes. So both of these problems had the same base exponent on both sides of the equation. And I'm only doing ones where you have an exponent on both sides of the equation because when you start including addition and subtraction, it gets a little bit more difficult because of how the exponent and log properties work or don't work with addition. Let's see, next I've got 8 to the minus x plus, that's a 14, equals 16 to the power of x. So here I've got different bases on both sides. So what I would need to do is, well, I would still take a log of both sides because I have things in the exponent and I want them out of the exponent, and that's what I would do. But this isn't the only thing I can do. Because if you notice, we have 8 and 16. Not only is one a multiple of the other, but they're both powers of 2 in this case. 8 equals 2 cubed. 16 equals 2 to the 4th. So instead of using logarithms, I can say that I've got 2 cubed raised to the power of minus x plus 14 equals, and then 2 to the 4th raised to the power of x. And I can simplify this using exponent properties. So exponents upon exponents turns into multiplication. And over here I'll have 2 to the 4x. And now I have the problem where I have the same base exponent on both sides. And so I could do log base 2 on both sides to cancel it. Let me rewrite this top. Minus 3x plus 42. Yeah, cool. Equals log base 2 of 2 to the 4x. Whoops. And these get to cancel because it's same base. And I'll have minus 3x plus 42 equals 4x. Add 3x to both sides. I get 42 equals 7x, or x equals 6. So we got another one. What if we have different bases on each side, but we don't get to see that they're both a power of a common base, we'll say. So here I've got 2 to the x plus 1 equal to 5 to the 1 minus 2x. So I have options here. not like I did with the previous problem, because 5's not some multiple of 2, 2's not some multiple of 5, they're not powers of some other number. But what I can do is I can choose any base logarithm I want and apply it to both sides of the equation. I could choose a log base 2, that'll cancel with the 2, but it won't cancel with the 5. Or I could choose a log base 5, which will cancel with the 5, but not with the 2. But what I do, anytime I'm not using a logarithm to cancel all of the exponents, when I have exponents of different bases, is I always use natural log. So I'll apply natural log to both sides. X plus 1 minus 2x. And then what happens is I apply the log properties. So here, exponent on the inside comes out, x plus 1 ln of 2. So now this is just a number. It's not any kind of function or expression or anything. And over here, I'll have 1 minus 2x ln of 5, which is, again, just a number. I don't know what number it is, but, you need a calculator to find it. And then I want to solve for x. So I think the best thing to do here is going to be distribute. So I've got x ln 2 plus natural log of 2 equals, and then natural log of 5 minus 2x natural log of 5. I'm going to get all of my x's together, and then all the extra junk away. So I'll put all the x's on the left. Let's see, so over here I'm subtracting natural log of 2, and I need to make sure I'm adding 2x ln of 5 on the left. Yes. So now I have x ln of 2 plus 2x ln of 5. And then what's left over here? Ln of 5 minus ln of 2. This is better than trying to do a bunch of division stuff, because now what I have on the left is I can factor out an x plus ln of 2 plus 2 ln of 5. So these are just numbers over here. Ln of 5 minus ln of 2. And then I can divide these numbers. So x is equal to the lovely number natural log of 5 minus natural log of 2 all over natural log of 2 plus 2 natural log of 5. That would be the exact solution answer. But again, we don't really know what that number looks like unless we pull out a calculator. But if you wanted, I guess, you could take this expression, plug it in for x in the equation at the top, and see that it works out to be the same on both sides. This is basically our key example for solving exponential equations. You could do this step for pretty much all of them. You do a natural log on both sides, and then you simplify, and you can solve for x after that, simply by distributing, gathering all of the x's on one side, and then simplifying further. But we've got one more. All of the ones we've done so far have been about, one exponent on the left, one exponent on the right. We don't have anything about when we have addition. So here's an addition problem. 9 to the x minus 3 to the x plus 1, right? Yes, plus 1 equals 0. So I could try to subtract the 3, or add the 3 to the x plus 1 to both sides so that I have one exponent on each side, but I still have this plus 1. And when I try to do natural log or something, I'll have a addition inside of the natural log. If you look at the log properties, we don't have a property for addition on the inside of a natural log. addition on the outside of logs turns into multiplication on the inside of logs, but we have nothing to work with addition in, so we wouldn't be able to simplify it or work with it. Our best bet for these kinds of situations is to try to think of them like they're a polynomial. So this one is specifically set up so that here, this is 3 squared to the x minus, and then I can rewrite 3 to the x plus 1 as 3 to the 1 times 3 to the x. Because multiplication among the same base of exponent turns into addition of the exponents. So I can work that backwards. Plus 1 equals 0. And then what I want to see is, I want to rewrite this. This is 3 to the 2x, or I can rewrite it as 3 to the x squared. And then I'll fill in the rest. 3 to the x plus 1 equals 0. And so we have something which is kind of like a quadratic. So let's relabel this. Let's call it z squared minus 3z plus 1 equals 0. And we want to try to solve this equation, which I don't think that factor is really cool. So we'll try a quadratic formula on this. We'll have z equal to b, no, we know what b is, minus b, so that's a 3, plus or minus the square root b squared, 9, minus 4 times 1 times 1, so 4ac, all over 2a, so that's just 2. I get z equals 3 plus or minus the square root, this will be 9 minus 4, so that's 5, all over 2. So there's my two answers for z. 3 plus root 5 over 2, and z equals 3 minus root 5 over 2. But that's z, and my z is equal to 3 to the x. So if I want to solve for x, because my problem is in x, so my answer should be x equals, I need to do log base 3 of both sides. And I'll get here x equals log base 3 of z, which means I have two answers. I've got x equals, oh boy, log base 3 of 3 plus root 5 over 2, and I have x equals log base 3 of 3 minus root 5 over 2. And those would be my answers here. One thing you should be careful of doing is right here, actually for both of them, you should check to make sure that neither of these answers is going to be a negative number. But I do know that minus or root 5 is going to be a number that is smaller than 3. So I know that both of these are going to still be positive answers. So we'll have more practice, I suppose, solving exponential equations when we get to our very last video, which is the last two sections, which are just some applications. One of them is money, which I don't like all that much, but another one has to do with growth and decay, and that's also something that gets repeated again in calculus. So let's move on to our logarithmic equations. So let's see, here I've got a log base 3 of 3x minus 1 equal to 2. Now what I would do for these actually is I would not raise both sides as an exponent, typically. The end result of doing that is the same as how I read these, but I try to avoid it. Instead, I use basically the definition of what it means to have a logarithm. I'd have the base raised to an exponent, and it's equal to whatever's inside. So this means that 3 squared is equal to 3x minus 1, which gives me a much easier problem to solve. I have 9 equals 3x minus 1, or let's see, plus 1, I get 3x equal to 10, or x equal to 10 thirds. If we use the calculator for that, we would have, I guess, 3.3 repeating. But our problems are not typically quite so simple. Let's see, which do I want to do first? We'll go ahead and do this one first. Let's say we've got log base 3 x squared plus x minus log base 3 x squared minus x equal to 1. Now here's one, well, I've basically just taken the previous problem, but I have multiple logarithms on the side here. But I still want to solve it the same way. So what I would do is I would use the log properties to combine the logarithms. I have a subtraction here outside between logarithms of the same base. That means division on the inside of the logarithm. So I've got log base 3, the division. So I've got x squared plus x divided by x squared minus x equal to 1. Now what I could do, well, let's just go ahead like we did in the previous. 3 to the power of 1 is equal to x squared plus x divided by x squared minus x. So I'm not doing any cancellation here. What I'm going to do is I'm going to multiply both sides by the denominator so that I don't have fractions to deal with. I'll have 3 x squared minus x equals x squared plus x. And we'll simplify this and collect everything on one side. Oops. So I'll subtract all of these over to the left. So if I subtract x squared, I'll get 2x squared minus, if I subtract this will be minus 4x equals 0. And I get the two solutions from factoring. 2x times what's left? X minus 2. So I have two solutions. I have x equals 0 and I have x equal to 2. But I don't really have two solutions. What you should always do is when you have your answers for your logarithmic equation, you should go up and look at the beginning, the very beginning part of the problem, and say, do either of these answers cause a problem in the individual logarithms? Well, if I plug in x equal to 2, I'll get log base 3 of, what was that, 6 minus log base 3 of 4 minus 2, 2. Those are both legal numbers. There's nothing wrong with those. But if I try to plug in x equals 0, then I'll have log of 0. And since 0 is not in the domain of a logarithm, log of 0 does not exist, doesn't matter what base you are, I can't include this answer at all. So I only have the one answer, x equal to 2, even though I had what would have been a quadratic. And that's a consistent problem with logs, is when you get an answer, make sure that your answers actually work inside of each of the individual logarithms of the original question. So what do we have next? Here I've got one with a log on both sides. So here I've got 3 log base 2 of x equal to minus log base 2 of 27. So this one won't work quite as well as the previous ones, where I just take the base, look at the right side, and set it equal to the inside of the logarithm, because I've got two logarithms. So there are two things I could do. Since I have the same base on both sides, I could put all the logarithms on one side and try to combine them. Or I could exponentiate both sides. Let's try to do both. So the first version will combine, but in order to combine, we're actually not allowed to have coefficients. So here I'm looking at 3 log base 2 of x plus log base 2 of 27 equals 0. I can't combine these because of the exponent because of the coefficient on this first log. So I have to use the log property that turns a coefficient into an exponent. And then I can combine these logs. Addition on the outside is multiplication on the inside. So this is log base 2 of 27x cubed equals 0. And then I can use the log definition to say that 2 to the power of 0 equals 27x cubed. But 2 to the 0 is just 1, which means x cubed is equal to 1 over 27, or x equals 1 over 3 as a final answer. Now another thing I could do, we call this exponentiation. So these are logs base 2. So I will raise both sides as an exponent of 2. So I've got 3 log 2 of x raised as a power of 2, and the other side raised as a power of 2 minus log base 2 of 27. And then what we have to do is we have to be careful here. So we've got 2 to the 3 times log base 2 of x equals 2 to the minus 1 times log base 2 of 27. Now I could do what I did over here. I could simplify each of my individual log parts by taking the coefficient and putting it inside as an exponent. But another thing I could do is I can rearrange using exponent properties. So I've got 2 to log base 2 of x, all of that raised to the power of 3, because exponents upon exponents gives you multiplication in the exponents. So I can rearrange, I could have 2 cubed to the log base 2 if I wanted, but I want it this way because I can cancel them. And similarly over here I'll have 2 to the log base 2 of 27 raised to the minus 1 power, and those will cancel, giving me x cubed equals 27 to the minus 1 power, or 1 over 27. And then it's solved just like it is on the other side. So just like with the exponents, we can have situations where we need to identify it more like a polynomial. So I could have natural log of x minus 3 square root natural log of x plus 2 equals 0. So this one looks particularly nasty, but we've actually had one kind of like this on a worksheet. We had an x and a square root, and we wanted to decompose it into component functions. So the thing we want to see is that if I take a square root and I square it, I just get whatever's inside. So I can look at this first term as the square of a square root. So this is natural log of x under a square root, and it's all squared, minus 3 square root of ln of x plus 2 equal to 0. And then I'll do what I did for the exponential, is I'll call it z minus 3z plus 2 equals 0, and I'll solve it as a quadratic. But this one factors. I can have, let me see, z minus 1 and z minus 2, I think. Let's check. I've got z squared minus 2 minus 1, and that's a plus 2. Perfect. So I've got two answers, z equals 1, z equals 2. But z is equal to the square root of the natural log of x, which means, let's see, z squared equals natural log of x, which means that x equals e to the z squared. Put the parentheses there so we don't confuse it for a different form. Which means my two answers are x equals e to the power of 1 and x equals e to the power of 4, which is 2 squared. Most of what we're going to be dealing with, though, is going to look like, whoa, that's too far. Like this problem here, where we have some combination of logarithms equal to a number. Because then we have to use log properties to simplify, and then we use the definition of the log to turn it into a more regular expression so that we can solve it. We have one last one to do, and this is the case when we have different logarithms. And this is something you hope you don't run into. Log base 5 of x equals, oops, I keep saying equals, plus log base 3 of x equals 1. So I chose very simple parts here, just because it gets kind of annoying. So the problem here is we have different base logs. So we can't combine them, and we can't treat them as any kind of like polynomial or anything because the bases don't have anything in common. So what I would need to do is use change of base. It might be ideal to choose to represent everything in log base 5 or everything in log base 3, but I'm going to change everything into natural log. So if you remember the change of base formula from the previous, I think it was a previous video, I'm going to be looking at natural log of x divided by natural log of 5 plus natural log of x divided by natural log of 3 equal to 1. And then to solve this, what I would do is I would get rid of the denominators, so multiply both sides by the common denominator. I would get, let me write it here. Ln of 5 times ln of 3, and the same over here. And the result of that is I would have natural log of 3 times natural log of x plus natural log of 5 times natural log of x equals natural log of 5 times natural log of 3. But the advantage here is now I've got numbers on the outside and I can just put them in as exponents and then I'll be able to combine my logs. We've got natural log of x to the power of ln of 3 plus natural log of x to the power of natural log of 5. And I could probably rewrite what's going on in there, but I don't want to. We could probably try to avoid it because I don't think it will help us right now. I can combine these logs now because they have no coefficients and they're a common base. So this is natural log of x to ln 3 times x to the ln of 5. And now this is a multiplication of exponents with a common base on the inside, and I can simplify that as well. I suppose another thing I could have done was to just up here simply factor out natural log of x. So what this means here is I have e to the ln of 5 times ln of 3 equals x to the ln of 5 plus ln of 3. And since I have my x simply by itself, I'm technically able to solve for x now, but it's not pretty. In fact, these are pretty much never pretty. But we can do a little bit. Let's see. I can use properties of logarithms on the right side. So this is e to the natural log of 5, natural log of 3, which is gross, equals, this is x to the natural log of 15. And then what I would do is find like the natural log of 15th root. What we do is we raise both sides, e natural log of 5, natural log of 3, raised to the power of 1 over natural log of 15 equals x to the natural log of 15 to the 1 over natural log of 15. And what that does is, because exponents on exponents like this turns into multiplication of the exponents, these will cancel, giving me just x alone. And then my answer is this e to the natural log of 5, natural log of 3 divided by natural log of 15. And I can't do anything to simplify that, so this is another really calculator answer. At any rate, these are all the cases we really have for solving our equations. Our big logarithm one really is this second example we did. We have a couple of logs that are maybe added or subtracted, so we use properties to combine them to turn it into the simple version, where we just use the definition to turn it into a more regular equation to solve. But I should point out, like we saw for the third one, when we have coefficients on our logs, we can't combine them immediately. So we have to bring the coefficients inside to make sure we've got plain logs before we try to combine them using the log properties, because the log properties are only stated for plain logarithms with no coefficients. So be careful when you're solving with these. And again, check your answers to make sure that they're going to be legal answers when you plug them in.